All right, so ODP 215, finding the largest node in the left subtree.
The screen.
Thank you. Ta-da! All right. So yeah, as we talked about yesterday, right? Basically, largest is past the root of the tree, so start at the left subtree's root arrow left, which we know exists, so we don't have to see if it's null. And if that points to something on the right, move to whatever it points to and keep going. So we exit that while loop when root right is null, at which point root is the rightmost node, and so we just return its data. So a question has come up, which is, do we need to have this structure statement in this function?
Yes.
Why?
Because it's treated as a global variable.
Effectively, it's not actually a variable, it's a declaration, right?
It's a declaration of a structure.
Of a structure, right.
So otherwise that we don't know what a struct node is.
Yeah, if we don't define the struct node in here, this will not compile. So, let's do an example. I have not tried this, so this might all be for nothing. It might just blow up in the end. Okay, so I'm going to say struct stuff n, and then I'm going to say my function n. I'm going to say n dot x equals 10, n dot y equals 20. So we get a little break from arrows for a few minutes. All right, so I'm defining a structure called stuff. It's got two pieces, x and y. They're both integers. I make a structure stuff called n, set x to 10, y to 20, and I pass that to my function. And that compiles just fine, other than I didn't prototype.
It had a capitalization in your declaration.
What I did not like? Oh.
Does my function take a struct stuff or a struct node?
I think you declared struct after the function.
That's what happens when you play without a safety net. All right, so like I said, that compiles perfectly on the first try. So let's make my function. So if we don't define this struct stuff in here, right, it cannot compile. It doesn't know what a struct stuff is. And even if we compile it with main.c, it still doesn't know what a struct stuff is. So this is something to keep in mind when we're compiling. This isn't exactly what happens, but you can think of this as being what happens. Main.c gets compiled into main.o. myfunc.c gets compiled into myfunction.o. And then these two get linked together into main. Okay, it's main because that's what we said after -o. So this is compile, and this is really linking. When we compile myfunc.c, it doesn't care about main.c. It doesn't look at it, it doesn't sneak inside and see if there's a definition of my struct, right? It's only compiling the code that's in here, or anything that I number sign include. So if I had a file that defined that struct stuff and I put that in a .h and I included that .h, I'd be fine. But the simple fact that I'm compiling alongside something that defines that structure doesn't help me with compiling this. Okay, you got to have it actually defined inside.
The programs are individually defined.
They're individually defined, yeah, unless you include stuff. Now there's stuff defined in stdio.h that's available to both of these because I included it in both of these. Right, so now I can compile everything up. And if I run that, it tells me I set my x to 10. So let me do the following. This is the part I haven't tested, but I'm very confident. In this function, I'm going to define my structure stuff. I'm going to declare y first. And when I run this, it's going to tell me x is equal to 20. So there's the main program on the left, there's my function on the right. Right, and I'm clearly in my main program, I'm setting x to 10, but in my function, when I print out n.x, it's printing 20. And that's not surprising, because when this stuff gets compiled into assembly language, it forgets about the structure statement. It doesn't think n.x, n.y, root arrow next, root arrow left. It doesn't think any of that. What it thinks is, if I say n.x, it thinks, okay, take the address of n and tell me what's at that location. Because when I say on the left, struct stuff, integer x, integer y, it's getting ready to create this variable n, and it's going to store x in the first 4 bytes, and it's going to store y in the next 4 bytes. And so when my main program says set n.x equal to 10, that compiles into assembly language code which says go to the address where n is and put a 10 right there. And when I say set n.y equal to 20, the assembly language code is find the address of n, add 4 to it, store a 20 there. There's where n is stored, add 4 to it brings me down here, that's where it puts a 20. In my function, I said integer y, integer x, so its view of what this structure looks like is like this. And over here, when I say print n.y, it says find the address of n and print what's at that location. When I say print n.x, that's what I said, it says go to the address where n is, add 4 to it, print what's at that location. Well, what did we store at 4 bytes past location n? We stored a 20. And there's no way that this code can know that n.x should be the same as what n.x that I used over in main. And in some sense, once you compile your code, these things are no longer part of the picture. So anything that you're depending on having been written in here that didn't end up in the main.os is gone, including the order of the fields in your structure. I was going to do this ahead of time and I didn't, so I may have to do this part tomorrow.
What's -s?
-s says, give me the assembly language code.
Oh.
So here's the assembly language version of my function. And yeah, that's going to be too hard to figure out what it's doing. Yeah, I'm not even going to try, especially with the camera on. But we can go through this another time, and we can actually see the assembly language and see where the main program was storing a 10 up here, and my function was trying to read it from this spot down here. Yeah?
Alternatively, we could always try to -s switch the hello world program.
True. And hello world's still pretty big when you look at the assembly language. So actually, here's an exercise. If you want to do this, so there's my function, right? Go ahead and compile that with a -c-uppercase-s, save your output, and then switch the x and y around in your structure statement, recompile it, save that output, see what changed in the two assembly language programs. And that'll show you exactly where it's referencing those fields. All right, so that's a bit of a sidebar, but it's topical. So one other thing I want to talk about before we get back to trees. This is for PA3. I've had the question come up multiple times on handling this business of what mode you're in, being in stack mode or being in queue mode, and there's different ways to do this, and some people are doing this by writing a bunch of if statements that correspond to stack mode and a bunch of if statements that correspond to queue mode, and sit in a loop until you say you want to be in queue mode, and then start executing this other loop until you say you want to be in stack mode. And you can do that, but let me re-explain my suggestion of a state variable, because this is something I really want you to come out of Clark with a good grasp of stateful programming. So here's the idea I'm suggesting. Make yourself a state variable. Okay, in 250 this is a bunch of flip-flops. For us it can just be an integer or a character or anything that can hold some value. And I'm just going to call an integer named state, and I'm going to give it a 0. And when I put a 0 in state, that means we're in stack mode. And if I put a 1 in state, that's going to mean we're in queue mode. And in my main loop, while 1, I'm going to read input from the user. And you're probably writing statements something like this. If input is the letter P, well, we want to either pop from the stack or remove from the queue, depending on what mode we're in. How do we know what mode we're in? Check your state variable. So if state is 0, pop the stack. If the state is 1, remove from the queue. if the user types a number, if they type an integer, we either want to push that onto the stack or we want to insert it into the tail of the queue, right? And again, how do we know which to do? Check your state variable. So if your state is 0, push your number. If your state is 1, insert your number into the queue, right, or push it into the stack, and so on. And then how do we change states? If your input is S, set your state to 0. And remember, whenever you go into whenever you specify a state, you want to print the corresponding data structure. So print the stack. And if the input is a Q, set your state equal to 1 and print the Q, and so on. And so this is the state machine, right? It's like the stuff we did in 250. This variable state is taking the place of the flip-flops. We have one set of code, but depending on the value of that state, the code does different things, right? And there's no magic, we just use some if statements. And this is what a state machine is. It's a fixed set of hardware, but sometimes that hardware is changing a light from green to yellow. Sometimes it's changing a light from red to green, right? It depends on the state, the value of these variables. In this case, one integer. And it's a really powerful approach to programming because it lets you basically have multi-purpose code inside a single loop that each time you go through might do something slightly different. And it's a very controlled way to set this up, and each of these blocks could have a switch statement. You might switch on the state and do one of 7 different things depending on which of 7 states you're in. And one other comment on here, magic numbers, not a good idea, okay, especially at 3 in the morning. State is 1, is that a stack or a queue? I don't remember, let me check my notes, So a better way to do this might be with a character, and you can set it to either the character S or the character Q, and that's a little better. But your other option, remember in C we can define symbols. So we can say number sign define, and we could define the symbol stack to be a 0, and we could define the symbol Q to be a 1. And up here when we initialize, we could say integer state equals stack. And down here in this if statement, we could say if state equals stack, or if state equals Q. Right, and that's really hard to get confused on. Right, that's clearly a Q, that's clearly a stack. And these values don't really matter. You could pick 12 and 13 or 200 and -76 or something, as long as they're unique values. But then if you want to have multiple states, you can just come up with symbols for each of them and use different values for each one. You could throw in a debug state, you could throw in an anti-Q state or whatever. So just some things to keep in mind as you're wrapping up PA3. All right, let's talk trees. So our goal here is to, for now, just insert things into trees, but preserve the balance of the tree. We want our tree to stay pretty full, pretty evenly distributed on the left and right sides. And you remember the recursive definition of whether or not a tree is balanced? There's three things that have to be true.
Both sides of the tree have to be less than 1 height difference.
Okay?
Less than or equal to 1.
So the height of the left and right trees have to be within one of each other. All right, what else?
The left side of the tree and the right side of the tree is balanced.
Yeah, the left tree is balanced and the right tree is balanced. Good, I didn't have to pull out my wad of $1 million bills. So it's a recursive definition, because to know if the left subtree is balanced, we got to use the same balance notion. And the idea is we're going to start with a balanced tree, and each time that we insert something, we're going to see if it's still balanced. And if it's not, we're going to correct that situation right then. So the tree's never going to get too badly imbalanced. Now, if someone hands us a tree and it's a big long line of nodes that's really just a slanted linked list, we can't use what we're going to talk about to balance it. But if we've got a tree that's balanced and we add one node and it gets a little lopsided, we can correct that lopsidedness using these techniques we're about to talk about. And so what we're talking about are something called AVL trees. I probably don't have a web page. I said last time that I should tell you what AVL stands for, because I forgot to look it up ahead of time. It's three people's name. Adelson, Velsky, and Landis. There you go. And this was done in 1962, so it's almost as old as me.
How old are you?
What?
Nothing.
All right, so AVL trees. So AVL trees, they're still binary search trees. Everything on the left is smaller than the root. Everything on the right is bigger than the root. Okay, and they're binary. You have no more than 2 children. But they have this notion of balance. So let me put up a sample tree. So we're going to define what we call a balance factor. And the balance factor is defined for each node. So for each node n, the balance factor of node n equals the height of n's left child minus the height of n's right child. No absolute value here. So it's the difference between the left and right subtrees' heights. And as a reminder, I'll put these on the board. So a null tree, what's the height of a null tree? -1, good. Single node? 0. Tree like this is going to have a height of 1. Tree like that's also going to have a height of 1. Tree like that's going to have a height of 2, and so on. So we'll just keep those as back of our brains. All right, so what's the balance factor of this node 60? What's the left subtree of this node? Null, and what's the right subtree? Okay, height of a null is -1. Height of the null on the right is -1. Subtract those. What's -1 minus -1?
0.
That's 0. Okay, so I'm going to put balance factors in parentheses. Okay, what about the 40? Say again? Almost. So the left subtree is null, so that's definitely got a height of -1. The right subtree of that node 40 is this tree. It's a single node, right? Single node has a height of 0. So negative 1 minus 0 is minus 1. Okay, what about the balance factor of the 20? Yeah, so left subtree looks like this. That's got a height of 0. Right subtree looks like this. That's a height of 1. Subtract. That's minus 1. And the 10 is going to be 2 nulls, so that's going to be 0. So we can write down the balance factor for every node in a tree. Okay, here's the deal. As long as all of these factors are 0, 1, or minus 1, we're okay. The tree is still balanced. But when we insert a node, if we find a balance factor of 2 or minus 2, the tree is unbalanced. So if all BF equals minus 1, 0, or 1, the tree is balanced. So this tree is still balanced. So let's insert an 80. And let's see what we end up with. So it's got to go to the right of 60. So there's our tree. So this is still a balance factor of 0. This is negative 1. This is going to be minus 1 minus 1. This is going to be a balance factor of minus 2. So we're going to add a node. We're going to move up towards the root and calculate balance factors. As soon as we find something that's 2 or negative 2, we can stop. And we know that we just did something that made this tree unbalanced. And the imbalance is somewhere between that minus 2 and the node we just added. So here's what we're going to ultimately do. If we think of the 40, the 60, and the 80 as being, the beginning, the middle, and the end of this collection, we want to preserve this order. We want 40 to come before 60, before 80. We're going to do what's called a rotation around 60. We're going to basically take that 40 and we're just going to bring it down to be on the left of 60, and we're going to let 60 come up and take the place of 40. So we had 40, 60, 80. We're going to change it like this. 60 is going to go up here. It's going to be 60, 80, and 40. And so this whole tree is going to change into the following. It's going to look like that. And this last one is going to have a balance factor of minus 1. So that's all going to be balanced again. All right, so it turns out there's 4 kinds of these adjustments we're going to want to do. What we just did was something called a right-right case. And we know it's a right-right case because we had a node with a balance factor of minus 2, and its child had a balance of minus 1. That's this case. If you have a minus 2 and the child is either minus 1 or 0, this is the case we're in. And there's a prescription here, an algorithm for how to turn this into that. And this will be balanced. But if we had the minus 2 and its child had a balance factor of 1, we have to first do a preliminary rotation which will make this look like that, and then we're in the right case and we can do our adjustment to turn this into a balanced case. And there's a symmetric pair on the left if our imbalance factor is positive 2 instead of negative 2. There's a left-left case and a left-right case. So right means that at this point there's too much stuff on the right, and if we look at the child, there's potentially too much stuff on the right of that. Right-left means there's too much stuff to the right of the root, but if we look at the right subtree, it's a little heavy on the left. And so our first adjustment is to make this so that it's weighted on the right, and then we can perform this change. So how do we interpret these pictures? So these nodes are labeled with the numbers 3, 4, 5. And there's these triangles A, B, C, D. These represent subtrees. We don't change anything inside those subtrees. They just go along for the ride. So node 3 is the node that's imbalanced by -2. Node 4 is its right child. Node 5 is 4's right child. And then each of those may have subtrees. Those could be null. In fact, in our case, they're going to be. And the idea is, if this is what our tree looks like that's imbalanced, we're basically going to change 4 to be the root. 3 is going to come down to be the left child of 4. But 4's already got a left child B. What are we going to do with that? 3 is going to adopt it on the right. So 3 will come down to be over here. B will take on 3's right child, which used to be 4. Node 5 just stays on the right of 4, and its children are unchanged. So let's try this for this case up here and see if we actually end up with the tree that I claim we end up with. So let me put this back here. 20, 10, 40, 60, 80. And this was a balance factor of -2 and a balance factor of -1. All right, so -2, -1, that's the right case. And I'm going to label these to match the labelings in this diagram. So node 3 is the node that's off by -2. That's this node right here. So this is node 3. And then node 4 is its child that's off by -1 or 0. So that's node 4. And node 5 is 4's right child. So that's node 5. And in this case, subtree A would be whatever was on the left of 40, which there's nothing. B would be what's on the left of 60, there's nothing. And C and D are 80's children. Right, so in this case, A, B, C, and D are all null. So that's particularly easy. And our rotation says make node 4 the root, put 3 on the left, put 5 on the right. So after we rotate, node 4, which is a 60, will be the root. Node 3, which is 40, goes on the left. Node 5, which is 80, goes on the right. These two nodes would adopt the children A, B, C, D, but those were all null, so there's nothing to do. And so we've replaced what was node 3, that's this node, with our new node 60, and the rest of the tree stays exactly the same. So this is still a 20, and that's still the 10. All right, and that's what I promised you we would end up with. Was the 20, 10, 60, 40, 80. All right, still with me? Yes?
Did you say this gets problematic if A, B, C, and D are not null?
Does not get problematic because they just go along for the ride. So in this case, C and D, they don't change at all. They're both 5's children. And A is still the left child of 3. The only change is whatever was the left child of 4 now becomes the right child of 3. And how do we do that? We just make one assignment statement. Because this whole thing could be a tree with 1,000,000 nodes, but it's got a root. And if we change 3 arrow right to be the root of whatever was 4 arrow left, we're done. We've taken this subtree and moved it to be over here. So coding these is easier than writing them on paper, actually. Okay, so let's take this tree and let's make it problematic, and let's see if I can get a right-left case. I'm going to insert a 35. I'll just do a 30. So I'm going to put a 30 down here. And I think that's going to give us a right-left case. So let's find balance factors. This is a 0. This is a 1. This is a 0. This is a 1. This is a 0. This is a -2. So let me redraw that. 20, 10, 60, 40, 30, 80. So balance factor of 0, 1, 1, -2. Okay, -2 because the left subtree is just a 10 that has a height of 0. The right subtree looks like this. That's got a height of 2. So 0, -2, -2. The 60 left subtree is 2 nodes. That's a height of 1. Right subtree is just a root. That's a height of 0. 1 minus 0 is 1. So the -2 tells us we're unbalanced. And the child having a balance of +1 tells us we're in this right-left case. So we have to do 2 of these adjustments, these rotations. So let's label these. So this is node 3. This is subtree A. This is node 5. This is subtree D. This is node 4. This is subtree B. And C is null. Does that look right? All right, so I'm just matching this picture. So node 3 is the place where you have the imbalance of -2. Left child is what we're calling A. Right child we call node 5. Left is 4. Right is D. Left of 4 is B. Right of 4 is C. So we don't need to be very creative here. We just need to kind of blindly follow this prescription. What we want is to have node 3 still be the root. So that's a 20. The thing on the left of that should still be node A. So that's a 10. But the thing on the right of node 3 should now be node 4. That's our 40. The thing on the right of node 4 should be node 5. That's our 60. Left child of 4 is still B. So that's still a 30. Left child of 5 is C. That's a null. And the right child of node 5 should be D, which is our 80. So that's the result after our first rotation. And if we find balance factors, we find -2 and its child is -1, so we're in the right case. Because the left subtree is a single node, that's a height of 0. And the right one is a tree that looks like this, which has a height of 2. Right, 1, 2, hops to the deepest node, so 0 minus 2 is -2. And these are still named the same as they were, so if we had assigned these to variables, nothing would have changed. So this is B, and this is 5, and this is D. And remember, these ABDs, these could be whole trees themselves with lots of stuff hanging off of them. That's okay. We're just moving them around. We're not changing anything inside. So now we have a right case, because we got a -2 and a -1. And our algorithm says, take node 4, make that the root, so that's 40. Put node 3 on the left is 20. 5 stays on the right is 60. 3's left child is still subtree A. 3's right child is now subtree B, that's our 30. And then node 5, which is our 60, left child should be C, which is null, and right child should be D, which is 80. And if we calculate this, it's nicely balanced. This is still a binary search tree, 10, 20, 30, 40, 60, 80. All right, everything's still in order. Yeah.
Why is a balanced tree important?
Oh, good question. When we think about things like our recursive insert function or our recursive delete function or so on, we're basically starting at the root and we're moving down. And the number of times we have to iterate either recursively or in a loop is basically bounded by how many times we have to step down from the root until we're done. And typically we're done when we run out of nodes or when we get to a leaf. So how many steps does it take to get from the root of a tree to a leaf? That's the depth of that node. And the maximum depth is the height of the tree. So if we have trees with a small height, we have a small amount of work we have to do for whatever we're trying to do. So how do we keep the height small? By making the tree nice and wide and fluffy. So a balanced tree is basically a way to minimize the height of the tree. And that takes some work to, I think, to show that balancing brings the height down. But the pathological picture of a tree that's a big long line of 100 nodes that just keep getting bigger and bigger, right, is the extreme end where the height of the tree is 100 and it's got 100 things in it. If we made it nice and short, we could have a tree of height 7 and it would have 127 things in it. So it's a nod to efficiency. All right, so one thing we haven't done is guarantee that these operations preserve the fact that this is a binary search tree. And that's fairly straightforward because of the way they named these. So let's look at our first tree, which is set up like this. And let's look at the traversal order. So we're starting at the root if we're just doing left node right in order traversal. First thing we're going to do is traverse the left subtree. So we're going to traverse A in whatever order A gets traversed. Okay, it could print out a bunch of nodes. And then we're going to visit the root, and then we're going to traverse this right subtree, which is rooted at 5. Well, how do we traverse that? First we traverse the left subtree. How do we traverse that? First we traverse its left subtree, which will traverse B, and then we visit the root, and then we visit the root's right subtree. That's the traversal of this 3-element tree. And then we visit the root of this tree 5, and then we visit its right subtree. So this initial tree has this traversal order. If we transform it into this middle state, and we do our traversal, what do? Start at the root, traverse the left subtree, visit the root, and then traverse this left node right. So go down, visit the left subtree, then visit the root, and then traverse the right subtree, which means traverse the left subtree, visit the root, traverse the right, same order. And then if we change that into this balanced case, what's the traversal order here? Traverse the left subtree first, which means do A, root 3, B, then the root of the tree, and then the right subtree says do the left subtree, root, and right subtree, same order. So none of these operations disturb the ordering of the nodes. And since these are subtrees that we're not affecting, right, the traversal of that whole subtree is not going to change. Now, proving that this restores balance, that takes more work. We're not going to worry about that. But it does preserve traversal order. All right, so that's a pretty crash course introduction to AVL trees. But like I say, it doesn't take a lot of creativity. It's a matter of taking your tree, insert a node, calculate the balance factors. If you find a 2 or a -2, see which of these cases you're in. Identify your nodes and your subtrees, and then just redraw your tree to match the corresponding picture you're trying to change to. If it's a left-right or right-left, you do that once to come into a left-left or right-right, and then you do that again to get it balanced. So tomorrow I will pass out your Valentine's Day balance sheets, and we'll have you go to the board in groups, and I'll just have you start inserting nodes into a tree, and you'll do these operations on it and get a hang of calculating balance factors and doing these manipulations. And then we'll talk a little bit about how you do this in code. But doing this in code is trivial, other than the details. But doing these kinds of things is laughably fun, right? It takes almost no work, and it's seriously easier than doing it on the board. All right, so we'll play around with that tomorrow.